People think physics is done. They imagine a big book somewhere with all the rules written down. We have gravity, we have electricity, we have atoms. It seems like we've figured out the basics. But that's not true at all. The truth is, the more we learn, the more we realize we don't know. The book of physics has more blank pages than written ones, and the things we don't know are the biggest things. They are the deepest questions about reality itself. We have two incredibly successful theories that describe the universe. One is general relativity. This is Einstein's theory of gravity. It describes the big stuff. Planets, stars, galaxies, the curvature of space-time. It works perfectly for just about everything we can see on a large scale. The other is the standard model of particle physics. This describes the small stuff. It tells us about the particles, like quarks and electrons, and the forces that govern them, like electromagnetism and the nuclear forces. The standard model is maybe the most precisely tested theory in all of science. It makes predictions that match experiments to an absurd number of decimal places. So we have one theory for the big and one for the small. The problem is they don't work together. They are written in different languages. When you try to use them in the same place, like inside a black hole or at the moment of the Big Bang, the math breaks down. And it gives you nonsense answers, like infinity. This is the central, giant, unsolved problem in physics. Finding a single theory, a theory of everything, that can unite gravity with the quantum world. But that big problem is made up of a whole lot of smaller, equally baffling problems. These are the cracks in our understanding, the clues that tell us we're missing something huge. Let's start with the big stuff, the cosmic mysteries. When we look out at the universe, we see galaxies. We can measure how fast they spin. A galaxy is just a collection of stars, gas, and dust, all held together by gravity. The stars farther out should spin slower than the stars closer to the center, just like the outer planets in our solar system move slower than the inner ones. It's a basic rule of gravity, but that's not what we see. When we look at galaxies, we see the outer stars moving just as fast as the inner ones. It's like the outer horses on a merry-go-round, keeping pace with the inner ones. The only way that could happen is if there's a lot more mass and therefore a lot more gravity than we can see. The visible stuff just isn't enough to hold the galaxy together at those speeds. It should be flying apart. This missing mass is what we call dark matter. We call it dark because it doesn't seem to interact with light. It doesn't shine, it doesn't reflect, it doesn't block light. It seems to just sit there, exerting gravity. And there's a lot of it. Based on our calculations, about 85% of all the matter in the universe is dark matter. All the stars, planets, asteroids, and glowing nebulae you see in pictures from the Hubble telescope make up only a tiny fraction of what's actually out there. We are the afterthought. So what is it? We have no idea. For decades, the leading idea was that it was some kind of new heavy particle that we just haven't detected yet. They called them WIMPs, or weakly interacting massive particles. Scientists have built incredibly sensitive detectors deep underground, shielded from all other radiation, just waiting for a WIMP to bump into an atom and give us a signal. But they've found nothing. Years and years of searching have turned up zero. So now people are looking at other ideas. Maybe it's a super light particle called an axion. Maybe it's a whole family of hidden particles. Or maybe, and this is the really wild idea, our theory of gravity is just wrong on cosmic scales. Maybe there is no dark matter and we just need a new Einstein to fix our understanding of gravity. But for now, it's one of the biggest and most embarrassing holes in our knowledge. The universe is mostly made of something we can't see and can't identify, and it gets worse. Matter, both regular and dark, has gravity. Gravity pulls things together. So you'd expect the expansion of the universe, which started with the Big Bang, would be slowing down. All that matter should be pulling on itself, acting like a brake. For a long time, that's what everyone thought. The big question was whether it would slow down enough to stop and collapse back on itself in a big crunch, or just slow down forever. Then, in the late 1990s, two teams of astronomers were looking at distant supernovae to measure how much the expansion was slowing. They found the opposite. The expansion of the universe is not slowing down, it's speeding up. This was shocking. It's like throwing a ball into the air and watching it suddenly shoot upwards faster and faster. Something is pushing the universe apart. There is some kind of energy inherent in the fabric of space-time itself that has a repulsive anti-gravitational effect. We call this dark energy, and if you thought dark matter was a big deal, dark energy is the real boss. It makes up about 70% of the entire energy density of the universe. Dark matter is about 25%. The normal matter that we're made of is less than 5%. So all of human history, all of our science and art and conflict has played out on less than 5% of what the universe is. What is dark energy? Again, we have no good answer. The best idea we have comes from quantum mechanics. In the quantum world, empty space is not empty. It's fizzing with virtual particles that pop in and out of existence all the time. This activity should give space its own energy. It's called vacuum energy. When physicists try to calculate how much vacuum energy there should be, they get a number. When astronomers measure the effect of dark energy and calculate how much energy is needed to cause the cosmic acceleration we see, they get a number. Well, these two numbers should be the same. They are not. They are different by a factor of 1 followed by 120 zeros. This has been called the worst theoretical prediction in the history of physics. It's not just a small error, it's a catastrophic failure of our theories to describe reality. We don't know if dark energy is a constant property of space or if it changes over time. We don't know what it is, and we don't know why our best theories are so spectacularly wrong about it. These cosmic puzzles lead to another one. When we look at the universe, it looks remarkably uniform. If you look at one patch of the sky and measure the leftover heat from the Big Bang, the cosmic microwave background radiation, it has a certain temperature. If you look at a patch on the complete opposite side of the sky, it has almost the exact same temperature. This shouldn't be possible. These two regions are billions of light years apart. They have never had time in the entire history of the universe to be in contact with each other, to exchange heat, and even out their temperatures. Light from one side hasn't had time to reach the other, so how did they know to be the same temperature? The most popular explanation is called cosmic inflation. The idea is that in the very first fraction of a second after the Big Bang, the universe underwent a period of mind-bogglingly rapid expansion. It grew from smaller than an atom to bigger than a galaxy in an instant. This would have stretched a tiny uniform patch of space out to become the entire observable universe we see today. It's a neat idea and it solves a lot of problems, including this temperature problem. But we don't know what could have caused this inflation. What was the inflaton field or particle that drove it? And what turned it off? Inflation seems to explain what we see, but it feels like we just invented one mystery to solve another. Then there are black holes. These are where our two great theories, general relativity and quantum mechanics, collide head-on. According to Einstein's general relativity, a black hole is a singularity, a point of infinite density, where the laws of physics break down. Information that falls into a black hole is trapped forever. It can never get out. But according to quantum mechanics, information can never be truly destroyed. It can be scrambled and rearranged, but the fundamental information about a particle's state must always be preserved. So, what happens when a particle falls into a black hole? Does the information disappear, violating quantum mechanics? Or does it get out somehow, violating general relativity? Stephen Hawking came up with a partial answer. He showed that due to quantum effects at the edge of a black hole, they aren't completely black. They should emit a faint glow of radiation, now called Hawking radiation. Over immense periods of time, this radiation causes the black hole to lose mass and eventually evaporate completely. But the radiation that comes out seems to be random. It doesn't contain the specific information about what fell in. So, when the black hole is gone, where did the information go? This is the black hole information paradox. It's a deep fundamental conflict between our two best theories of reality. Solving it would likely be a huge step towards a theory of quantum gravity. This brings us down to the small scale. The biggest unsolved problem of all is the one we started with quantum gravity. We need a theory that can describe how gravity works in the world of particles. We need to know what happens at the singularity of a black hole or at the moment of the Big Bang. There are two main attempts to build this theory. One is string theory. It suggests that at the most fundamental level, particles are not points. They are tiny, vibrating strings of energy. An electron is a string vibrating in one way. A photon is a string vibrating in another. All the different particles and forces we see are just different notes, played on these fundamental strings. It's an incredibly elegant and mathematically beautiful idea, and one of its notes corresponds perfectly to the graviton, the hypothetical particle that carries the force of gravity. The problem with string theory is that for the math to work, the universe needs to have extra dimensions of space, maybe 10 or 11 in total, that are curled up so small we can't see them. And so far we have no experimental way to test this. We can't see the strings or the extra dimensions. It's a powerful idea with no evidence. The other main approach is loop quantum gravity. This idea takes a different path. Instead of trying to quantize gravity on a smooth background of spacetime, it tries to quantize spacetime itself. And it says that space and time are not smooth and continuous, they are made of tiny, discrete chunks or quanta. There's a smallest possible length, a smallest possible area, and a shortest possible time. You can't zoom in forever. At a certain point, you hit the fundamental pixels of reality. In this theory, space-time is a network of these interconnected loops. The properties of this network give rise to gravity and the universe we see. Like string theory, it's a fascinating idea, and like string theory, we have no way to test it yet. The scale at which these effects would be visible is far, far smaller than anything we can probe with our current technology. Even within the standard model, the theory we know works so well, there are deep puzzles. One of them is called the hierarchy problem. The standard model describes four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, which holds atomic nuclei together, and the weak nuclear force, which is involved in radioactive decay. The problem is that gravity is ridiculously weak compared to the others. Think about it. You can pick up a paperclip with a tiny refrigerator magnet. That little magnet is overpowering the gravitational pull of the entire planet Earth. Why? Why is gravity so many trillions of times weaker than the other forces? It seems so out of place. We don't have a good reason for this huge discrepancy. It's like having three people who are about the same height, and a fourth person who is a million miles tall. It just feels wrong, like it's a clue to some deeper physics we don't understand. And there's the nature of quantum mechanics itself. It's a theory of probabilities. It tells us that a particle, like an electron, doesn't have a definite position until you measure it. Before that, it exists in a superposition of all possible positions at once, described by something called a wave function. When you look, the wave function collapses and the particle picks one spot. This is called the measurement problem. What counts as a measurement? Does it require a conscious observer, a machine? What is the physical process of this collapse? The founders of quantum mechanics basically said not to worry about it. The math works, so just use it. This is the Copenhagen interpretation, but many physicists find this deeply unsatisfying. It leaves a weird gap between the quantum world and the classical world we experience. Other interpretations have been proposed. The many worlds interpretation suggests the wave function never collapses at all. When you make a measurement, the entire universe splits. In one universe, you see the particle here. In another, identical universe, a copy of you sees the particle there. Every quantum possibility plays out in a separate, parallel universe. It sounds like science fiction, but it's a serious attempt to solve the measurement problem. The trouble is, we can't access these other universes, so how could we ever prove it? The fundamental question of what quantum reality is remains unanswered. We have the rules for how to use it, but we have no consensus on what it means. Then there are problems that are less philosophical and more concrete. The standard model predicts that particles called neutrinos should have no mass. For decades, this seemed to be true. But experiments, particularly ones studying neutrinos coming from the sun, showed something strange. Neutrinos come in three flavors, and they seem to be able to change from one flavor to another as they travel. According to the rules of quantum mechanics, this is only possible if they have mass. So neutrinos do have mass. The standard model is wrong. It's not a huge error, but it's a clear, undeniable crack in our best theory of particles. We've measured that they have mass, but we don't know how much they weigh or why they have mass at all. Figuring out the source of neutrino mass could point the way to physics beyond the standard model. And finally, there's one of the most basic questions you can ask: why are we here? Not in a philosophical sense, but in a physical one. According to our theories, the Big Bang should have produced equal amounts of matter and antimatter. Antimatter is just like regular matter, but with the opposite charge. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of energy. So, if the early universe had equal amounts of both, they should have all found each other and wiped each other out, leaving behind a universe filled with nothing but light. But that's not what happened. We live in a universe made almost entirely of matter. All the galaxies, stars, and planets are matter. We almost never see antimatter in nature. Something must have happened to create a tiny imbalance in the very early universe, something like one extra matter particle for every billion matter-antimatter pairs. That tiny leftover amount is what formed everything we see today. We know there are subtle differences in how some particles and antiparticles behave, a phenomenon called CP violation. But The amount of this violation that we've measured in our experiments is nowhere near enough to explain the sheer dominance of matter in the cosmos. Where did all the antimatter go? Why does a universe of matter exist at all? It's a profound question, and the answer is still out there. These are just some of the big ones. There are others, like the nature of time's arrow, the existence of magnetic monopoles, or the reason for the specific values of the fundamental constants of nature. It can feel a bit overwhelming, like our understanding is a tiny island in a vast ocean of ignorance. But that's what makes physics exciting. It's not a finished subject, it's an active, ongoing human adventure. We build giant machines like the Large Hadron Collider to smash particles together. We launch incredibly sensitive telescopes like the James Webb to look back to the dawn of time. We build gravitational wave detectors to listen to the echoes of colliding black holes. Each new discovery might answer an old question, but it almost always opens up a dozen new ones. These unsolved problems are not signs of failure. They are the roadmap. They tell us where to look next. They are the hints that nature leaves for us, pointing towards a deeper, more elegant, and probably much stranger reality than we can currently imagine. We don't know what dark matter is. We don't know what dark energy is. We don't know how to unite our best theories. We don't know the answers, and that is the best part. It means the story is far from over.